Thank you, Aaron. Welcome back to the session. I just wanted to take a couple of minutes where I wanted to follow up with what Frank started yesterday on the history of these sessions, basically. And actually, Avichal also alluded to this. The real-time sessions, we called it HREX later on. I think I've been associated with these sessions for almost 12 years now. And it started with JET system. And we have progressed from the JET to the cloud computing, which is very, very encouraging. The way we do this is Bob Gall, when he handed over the position to me and Vijay, he said, push the envelope of research. That's where the whole concept of it originated even earlier, the real time, but we keep pushing the envelope of research. And the one that you saw in ensembles is one of them, basically pushing the envelope of research. You have a few more coming up, like the Bayesian scale and stuff like that. But we need to keep in mind, and we need to discuss on Friday about fragility of some of these resources. For example, the ensembles that we ran. And it was, I have to mention this because it's more, not because it was done by me or something. It came out of a discussion that I had with Frank Individual while going in a train from GFDL to DC. He asked me, hey, can you come back and say that why you cannot use these resources, cloud resources? And then I talked to Aaron, I talked to Avichal, and things came together so quickly. But it also illustrates the fact that these resources are not going to be permanent. But at the same time, we do from OCIO, in thick and thin times, I would like to thank both Frank Individual as well as Radhika Subramanian. They will be here. They have been helping us, saying, hey, we have these resources. Can we, do you guys want to use it for hurricanes? So some of these, while pushing the envelope, we should remember that we need to have more sustainable resources for running this. For example, apart from all the people's time that we are talking about, this took about 1.5 million hours.
We need to go to the next topic.
Yeah. So with that said, I wish to go with Gus. With Gus and Bill. And yeah.
All right, thank you, Gopal, and good morning, everybody. Good to see a lot of faces I haven't seen in person in a couple of years. So yeah, this talk is going to be mostly on multiple. Bill has been doing a lot of the heavy lifting with the moving nest coding, so he's going to talk about some of the really nice advancements on the technical side. I'm going to provide sort of the big picture. So we're going to start out going through some of the motivation. But first, I just want to say, like, this effort, it extends to a lot of folks at AOML and EMC so far. So the collaborators are listed here, and of course, yeah, we wouldn't be able to make these efforts or these advancements without their work as well. All right, next slide, please. Yeah.
Right here.
Oh,
just the big green arrow.
Gotcha.
But you got your first one. So
All right, let me go back.
the little red.
Yeah, okay. So yeah, here's just a quick table of contents. So getting into the motivation. So moving nests, like I think everyone here is familiar with HWRF and the benefit that moving. On the left side, this is a figure I've been working on in a different paper, but looking at the progress of HWRF, the trends essentially in HWRF forecast errors over the lifetime of HWRF. And you can see that significant reductions in the intensity errors at all forecast lead times. This is showing every 24 hours. And really, if you look over at 2022, the forecast errors that you're getting for 120 hours forward and said, let's pick out the years that we had moving nest upgrades and see how the performance of the intensity did. So what we did is we looked at 2011 when there was it upgraded to 2 nests, 15 where the 2 nests were upgraded in resolution, and then another resolution upgraded in 2018. And what we saw in this right panel, this is skill. We saw a successive big jump in the forecast intensity skill. Not themselves just simply by increasing the resolution of the nest, but it enables a lot of other upgrades to the physics and other parts of the system, the DA as well. So what we did is we in our base multiple, yeah.
second? We may have to actually go out and come back into the meeting. We're getting a lot of audio pops at the moment.
Oh, okay. Maybe I'm too close to the,
It's possible. We're getting a ton of people in the chat saying they're having issues. So
okay. I don't want any injured eardrums, so.
Ask if that sounds better.
All right. Hey, how do I sound now? Okay. Okay.
yeah, keep going.
Okay, I'll continue to try
We
to,
drop the gain a little bit at this end.
I'll try to tone it down a bit on my side. So I get pretty excited. So the basin scale HFIP system is where we demonstrated multiple moving nests. So we went from a storm-centric approach where we just had a set of moving nests for one animation on the left is showing, nests that are covering multiple storms over the NHC area of responsibility in the Atlantic and East Pacific. And I put some hypothetical ones on there. The nests don't spawn mid-cycle, but just illustrating all the storms that we could be capturing. And we did a really careful systematic study where we said, what happens just when we add more moving nests to a configuration? So we started with our basin scale big domain, and we started with one nest, and we increased to 2 and 3 and 4 and 5. And what we found is just simply by adding more nests for storms, we got up to 10% improvements over the full sample. But we had really over 10% over the whole sample. And we also found some really interesting long distance signals where the improvements were up over 30%. So really interesting stuff. And this is the paper I worked on with Shujin and Gopal. With that, we said, we have the motivation. We really want to get this technology into HAFS. And so that's where Bill came in and really took it to the next level.
Thanks, Gus. So yeah, the next step that we've been working on has been multiple moving nests over the last year or so. Is the regional or basin sort of setup where we'll have multiple moving nests on a single parent grid. Another option is running multiple nests on the global configuration, so either on several storms in one basin on one cube face, or perhaps even on several cube faces. Each of these will have, the internal tracker running for each individual system. We have currently two-way storm feedback at 100% back to the parent grid. So any interaction between storms is mediated by, going through the parent grid first. And, to echo what Gus said, we leveraged a lot of existing work and code from multiple sources. So the multiple static nest work that had been done at GFDL by Joseph Mwalem and others, and the workflow by Bin and others at EMC has really been key to getting this to work. So at this point, we have the multiple moving nest code running for a number of cases. I've released the code to the rest of the basin scale team. They're starting to do a lot more testing. Where it stands at this point is the model code is running. So the cases are manually configured with cold starts, where I placed the nests at locations sort of manually with the offset X and Y. It's a fairly tedious project to do that. So hopefully soon we'll be having the upgrades to the workflow to handle, automatically placing those based on the storm, the ADEX and BDEX. But at this point, what we have basically is there's a number of cases for fast testing at a coarse C96 regional configuration with 2 and 3 moving nests, as well as a configuration of 1 static nest and 1 moving nest. And then also there's some high resolution cases that are based on the HAFS B configuration. So this is a C512 regional with 2 and 3 moving nests. So shown here is a case from 2020 with 3 active systems in the Atlantic. This is the HAFS B parent configuration, and each of the nests is the same as the HAFS B nest size. We just have 3 of them running at once. So it's 6 kilometer resolution for the in terms of where we stand on this code right now, we've tested up to 3. We're looking at doing tests in the next few weeks, hopefully for 4 or 5 and more nests. Basically, once we can get the workflow to do that in a more automated way. One of the things about the performance of this is that the code runs where the parent and each of the nests time step in parallel on separate sets of processors. This is something that's inherent to the F than what we were able to do in HWRF. So this is a better performing model in terms of speed for that, the way that's set up. In the high resolution nests will influence the environmental flow and the other, thermodynamic properties so that they can influence one another in a better way than running, the separate regionals. So this graphic was made with all the outputs from this run of basically the upward and downward radiations to show the visible and enhanced IR. Another piece of this one that I discussed briefly earlier is that running a static nest that I just sort of convenience placed in the northeast corner of the map, and then a storm following nest that's following Hurricane Laura from 2020. So this is also something that can be run, for if we want to focus in on a particular heavily populated area that you want to have high resolution all the time. One of the other things this shows is how the nest overlap handle will work, which is, one of the issues that you will have when you have multiple nests is they move nearby each other. We need to make sure that, number one, that it just runs. So that runs at this point successfully. The model doesn't crash when they do overlap. The way that it works right now is each one of those nests feeds back to the parent in a serial algorithm. So basically, the one that you've numbered as the highest numbered nest will be the one that overwrites that overlapped area. So this is a reproducible and reasonable answer. It's probably not the most optimal. So we're looking at some future work to try to blend the feedback from those nests. Some of the considerations in that, though, is how many processors have to be talking with one another for performance and worrying about deadlocking or something, as well as keeping all of the atmospheric variables internally consistent so that the model is stable. Moving on to one other set of work that we've been doing over the last several months. We talked at the UFS meeting in July with Avichal about getting the NOAA MP land surface model running. So this is now working, have this code checked into a feature branch for the HAFS v2. This involved adding 36 land surface variables. There's an illustration taken from one of the NOAA MP sites of some of the things that are considered in here. Did some upgrades to how the land masking of these surface parameters work, and also to how default values for isolated land points are set. So in the past, with the previous physics variable shifted, you could put a fixed value in as a default value if you, for instance, resolved a tiny island that was far away from any neighbors to give you information for something like, say, leaf canopy temperature or something. So now we have a variety of ways to handle that. One, we can set a fixed value for something like an albedo or an emissivity, or for these temperature values, we can use the skin temperature from that location. So that gives us a very physically consistent value for each of those. One other piece that was involved here was extending the vertical coordinates for some of these variables that are a little more complicated in the NOAA MP. So this is now going to be going into some testing and validation, so this will also be available. And now I'll turn it back over to Gus for the discussion of the HAFS basin work.
Thanks, Bill. All right, just a couple minutes at the end here to talk about our plans going forward. So this is a schematic showing our idea for the HAFS basin workflow. Just really quickly, the idea is obviously to get, to get to a configuration like this, where we have a large static parent domain that covers at least the North Atlantic basin. This is what we're thinking for this summer. And, at least two nests with it for at least two storms. And the way we're going to initialize the storms is we're going to have these sub workflows that are storm centric, so we can actually have the right information and fields to do the vortex initialization and data assimilation. we run into some issues, and we did an HWIRF where, say, this storm, if we wanted to initialize it, it's too close to the edge of this parent domain in order to get all the necessary data to separate the storm from the environment. So this is the way we're working to get around it. Lou is actually leading this effort on the workflow side. So we're excited to get a prototype of that together quickly. And like I said, hopefully run it in real time this summer. Involved in this development, we're going to be looking into the nest versatility. What's the number of nests? Where can we place the nest? Static versus moving. Bill just talked about some of the really nice upgrades that he's put into the code that will allow us to test this stuff. Testing the domain size limits of the ESG. This is about as big as we can make that domain, with the ESG projection. Thanks to Aaron. So, we're investigating, is this large enough for us to do some of our initial experiments? Absolutely. If we wanted something that parallels what we had with basin scale H responsibility with one domain, we have a little bit of work to do with this. And, we're asking the question, is it worth it to maybe in the future go to a new projection, or do we put our eggs in the global basket at that time, so to speak? I mentioned the sub workflows, and obviously a lot of work that we're going to be doing is this resource profiling. So increasing the number of nests and testing different domain sizes, figuring out what can actually fit into a reservation potentially next summer, but longer term, what are our options for research and going forward into potential operational implementation. So for the 2024 HREX experiment, 2 to 3 moving nests is what we're targeting. Ongoing R&D is that we're continuing to add more nests. So, Bill showed that we're successfully running with 3. We're going to add to that, looking at multi-basin domains, advancing the DA further. So we haven't talked about it much yet, but having a lot of conversations with Jason Sipple and others about how we can start to cycle this outer domain once we start running that. And really quick, something that is interesting is, this idea of a Genesis module that we're investigating, where we might actually be able to tap into the tropical weather outlook from the Hurricane Center and use that to place nests in advance of a Genesis event. So that's something that we're kicking the tires on and developing as well. So with that, I think I'll leave it there. And I had to, of course, show this animation. So here it is at the end. Thank you.
It's just, I think we'll postpone the discussions to the end.
We don't actually have a discussion period in this because you stretched them out to 15-minute talks, and that killed the discussion period.
Okay, so do we go with the question?
So we basically have to go into the next talk, or we're going to blow through everything in the afternoon.
Find me if you want to ask questions and talk more about it.
Yeah,
Okay.
I put in the chat to please reach out to the authors with pressing questions so that
Sure.
we can get back to you.
Sure. Next we get on to Fanglin and
give the first one and you will give the second part. First, I'd like to thank Gopal, reach out to me and say, hey, Fanny, can you give a presentation? Participation of the HFIP meeting. So far, I really enjoyed great talks and great location. Thank you all. So I gave a brief review of the physics development for HAFS, but not for HAFS, also for the overall the UFS community. So you all have said that so NOAA is developing the next generation operational models based on the unified forecast system, fully coupled. So for the UFS physics development, you can say our physics at least the EMC, GFS, also many other applications like even the air quality model and the space weather forecast model. But we all based on the same physics package, CCPP. CCP has many options. For the ultimate goal is to improve the physics for UFS applications to reduce model systematic bias and maximize model to reduce the cost and also make the transition to operation faster. I think we have made some success for unification, but there are still challenges. This is a past work, everyone just work on their own model, different physics, different dynamics. For the first time, we are unified, and we're trying to do the also Give you an overview, say what the physics and options has been selected or next for HAFS already in operation, others still in development. You can compare them, and for HAFS basically is based on largely based on the GFS version 16 physics. Of course, the targeted for the hurricane forecast. But likewise, if we put some of the development on the HAFS back to GFS, and we are not there yet, just out of the box, you can run any physics development in the HAFS and use in a global cost resolution model. The major difference between the GFS and HAFS is really in the macrophysics scheme. You can say that Thompson macrophysics using the HAFS-B, and there, other than that, the PPR schemes. So the RFS version 1 is not just based on the her physics, but it like AKM version 7 also based on not just based on the GFS version 16 physics. I pointed her development made for the first specifically for the GFS, but highlighted here a lot of the development in blue color. They have naturally been included in HAFS. We are using a new NAND model and replace the NOAA NAND service model with NOAA MP. As earlier the speaker mentioned, they will be tested in HAFS version 2 as well. We have the new small scale ground drag and turbulent orographic foam drag transition. Waking scheme, the Proglass SD scheme also mentioned by Andy earlier. New stochastic physics in ocean, land, and atmosphere. Positive definite tracer advantage scheme. This looks small but very important update for us for the global application. Otherwise, global mean precipitation will be 4 milliliter per day instead of 3.1 because the clipping of the negative tracers. We have the new capability coupling between the air source and also an introduction of Franklin grid and with a lot of changes for the land boundary conditions, land and ocean boundary conditions. Other improvements like convecting and boundary layer scheme, ground drag and mountain block, and also coupling of land model and the surface layer schemes. So this has been shown a few times. What's been used in HAFS and the test plan for version 2. I know their part is not all consistent. They're all it's under active development. Many options has been put into consideration, and for version 2 HAFS, like the NOAA MP MOM6, adjust the roughness length if needed for the surface layer and test. This so-called HR to HR3, the first high-resolution test of the GFS version 17 prototypes was they were counted. There's plan to include whenever they are like HR3 become available and the HAFS version 2 test we're using this physics package. Some of the updates include the wind shear effect and also high order terms. There's reference if you want those detail, you can click on this. And Thompson MP in HAFS, and we are trying to include the GFDR macrophase version 3 in the CCPP. It will take some time because the GFDR put in your dipole part. GFDR does not use CCPP. If you want to use it, you have to extra work to put them. But this work is ongoing. The Kum's convection scheme also doing a lot of tuning and also you update like the wind shear effect. We go has done a lot of tests for the wind shear effect on the convection scheme and sensitivity to entrainment rate and can use the TTIC scheme even for operation now. We get the approval. It took a while to communicate with the ECMWF value is agreed. We can use this version in CCPP. We may be able to use their latest version. ECMWF will probably open their source, become an open source code community, so anyone can use their code in the future, but it has not been finalized yet. Well, further, like also test on the community ground drag has not been included in HAFS. Important to trigger in non-station ground drag. Also other efforts to test different DICE options. Just go from only at 10-minute mark. Do I have?
We've got about 2 minutes.
Okay. So there we have done some of the sensitivity test for the physics update I mentioned earlier. One of them, like the convection, use the GFSL HR2 PBR scheme convection plus this Proctor sigma scheme. So in short, the impact is GFS HR2 physics gives better intensity than HAFS A, this written line, and a worse strength. The ending the Proctor result this mode test. Another example here is the test of Thompson MP in HAFS A. So overall, Thompson MP gives better intensity than HAFS A, but worse strength. And depending on the aerosol radiation tracking in HAFS A, also improve strength, but degrade the intensity and the RMS. Let's see. So there's a list of ongoing and or planned development activities. I'm not going to talk over them, and if you're interested, you can check them later. So there's a lot of physics updates to be considered. The final point I'll make is whatever will allow is a UFS community, whatever physics development within one application will be eventually test the event in other application. We're very careful not to say just make one change based on one application. We need to consider all applications because the impact is all across the board. I'll stop there. Thank you.
Thanks, Fei-Ling Lim. I'll try to keep this pretty quick. So I'll be talking about a little bit about the physics development and testing we've been doing in HAFS B. So one of the things that we're working on right now is, and kind of finishing up, is a set of sensitivity tests where we basically, in HAFS B, one of the two big changes, the Thomson microphysics and also the GFD, or the TC PBL, TC specific PBL options that I worked on with Xiaomin Chen. So I'm doing a set of sensitivity tests to basically do test each of those separately and compare with the 3-year retros for HAFS B. And what we found is that better intensity results for both. And in terms of, especially for RI and intensity bias, that's where we really see the TC PBL options showing improvement. So you have a lot better RI detection with these with the enhanced boundary layer structure. And so this is in a paper that's in its second round of review at Weather and Forecasting. Another thing, like Fei-Ling mentioned, we're starting to look at the convective scheme. Since we want to continue to improve the diversity and also the skill. So we're started a set of tests with the TDK convective scheme for Idalia and Lee. The track forecasts have been pretty promising so far, but there's several cycles that kind of missed the RI of Lee. So you sort of get a trade-off there. And like Fei-Ling mentioned, there's sort of a newer version that we may be able to get our hands on soon and see if that's any better. But certainly that's sort of something, when you make one thing better, sometimes make something else worse, and we want to improve this holistically. And finally, we want to kind of, especially at HRD, one of our big things is to in AOML is to compare everything we do with observations that we collect during our field program and things like that. So I showed a little bit earlier, how we evaluated some of our experimental and operational HAFS B with P3 data. So we're continuing to do that both for individual cases and then also like that composite study I was showing. We've been kind of comparing that with a composite of radar data to sort of illustrate produce sort of a 2 week of an outer vortex. So that kind of tells us that maybe HAFS in general is producing TCs that are too narrow. So sort of this comparison with observations, I think will be a way for us to sort of get into that sort of structure-based validation and diagnostics that kind of what Frank was talking about yesterday. So just, I'll finish quickly by talking about, we're continuing to evaluate and refine the PBL options. We want to continue to evaluate different convective schemes. TDK, we've done a little bit of testing with some of the Grafreda scheme working. Continue to improve it. Be working with Xiaomen on a project where we're looking at unifying the mass fluxes between the PBL and convective schemes and really get into how these schemes are linked. Because that's sort of, I think, another way that will take this to the next level. And you're not just treating them separately. So thanks.
Thank you, Andy and finally. We move on, and in the interest of time, we'll move on to the progresses in DA by Jing and Young-Hyu.
I don't know, we may have to advance your slides for you if you get Twitch computers. So the remote may not work. So
Okay,
we'll probably have to advance them for you.
all right. But the laser still works. The laser point.
The laser pointer will still work. Yeah.
Okay, that's great. This one?
Is it you? No, that's the next one. That's the
Yeah,
wrong one.
this is great.
Sorry about that. Okay. We good now?
Yes. Okay, so good morning. The topic here listed is the 2023 HAFS 1.1D real-time parallel experiment, which is a self-cycling 3D ensemble bar ENCAP hybrid data simulation system. But I will also talk about the current status of HAFS DA. And I would like to, are we sharing?
For some reason won't go full screen.
Okay, so I would like to thank for all the colleagues from EMC and the AOML, OU, and the UMD Hurricane Data Simulation team, as the HAFS DA system is a collaboration effort. I also want to give a special acknowledgement to my colleague, Dr. Yonghui Wong. He is the one who is conducting and monitoring the 1.1D real-time experiment for the whole time. So, okay, so to start with, I would like to show the overall workflow of current HAFS system and also talk a little about the DA capabilities. In this left-hand side, this workflow diagram, I know it's complex, but you just pay attention to this purple color component. Those are related to our DA. And for now, we have DA options of VI, FGI, and we rely on the GSI data simulation platform to perform the 3D bar, 3D ensemble bar, 4D ensemble bar, and ENCAP and the VAR ENCAP hybrid data simulation method. So if we're using ensemble bar data simulation, we can obtain the background covariance from either GDAS ensembles or HAFS ensembles, or from both. And the HAFS analysis is currently can perform either on the storm-based domain, or it can perform on the static domain, DA domain, if it's a self-cycled system. And right now, HAFS DA can assimilate observation, including the conventional observations, recon data, satellite-derived wind, satellite readings data, and TC vital data. So here, this one is compare the currently operational HAFS A versus the 1.1D DA workflow. So for the operational HAFS, we initialize our system from the GDAS, and for every 6 hours, GDAS is going to provide the initial conditions for the outer domain, and then the data simulation is going to perform in the storm-based domain here with the GDAS ensemble members as the background covariance, and we're using 4D ensemble bar and FGAT here. And for the HAFS 1.1D data workflow, the GDAS will only provide initial condition, initial ensembles for the first cycle, and after that, we will use the forecast the ensemble members from prior cycle to provide background currents together with the GDAS member for the statics domain. And we're using 3D ensemble R to do the analysis. So here, the GFS data provide the boundary conditions for both of the system. So this table summarizes the current observations can be assimilated inside DA. So including satellite radiance data, ozone data, and conventional observations, including from multiple instruments such as aircraft, soundings, RAS, surface data, video, wind, and also satellite image derived wind, as well as we also assimilate surface sea temperature, radar velocity, and also GPS RO data. And for this year, the HAFS using CRTM version 2.4.0 to do the satellite radiance data assimilation, but in the future, perhaps version here, but this data is not currently used in HAFS operational HAFS, but it's assimilated in the 1.1D data assimilation system. So here, this one is showing the conventional observation assimilated numbers for the entire life cycle of Hurricane Lee. So we can see about the P3 and J4 data, which indicated by the blue color or purple color here. And as it's approaching the land, we will see a lot of numbers from the next red radar. And the right-hand side is showing the innovations from the conventional observation data simulations. So here shows a snapshot while the Hurricane Lee is over the ocean or approaching the land. Actually already landfall. So you'll see the horizontal distribution of every types of observations here, such as P3, J4, and also drop sound along the flat track. And here you see a huge number of next red data here. So I know a lot of previous talks already kind of look into the HAFS performance. Here we just do this overall verification for all big forecast and the intensity forecast, and then compare it with GFS and the ECM-WF data. So overall, the track forecast of ECA is still the best, but also I would like to point out that after day 4 or 5, HAFS B and HAFS A managed to catch up, and especially for HAFS A, it's managed to perform a little bit better in tracks forecast. But again, this is for all the basins. And here the ECM-WF was only available. See there are less case number here, and also the track is calculated using the EMC tracker. And for intensity, the HAFS A, HAFS B overall is best. Next. So now I'm gonna moving toward to talk about more for this HAFS V 1.1D system. So first of all, this one is the object is we're trying to get a proof of concept of a self-cycled HAFS DA system with makes the HAFS and GDAS ensemble members. And but this one will not be in our HAFS V2 plan. And also doing this experiment, we try to test the DA capability of the 3D ensemble bar ENCAP hybrid functionality. And we also try to see if this HAFS DA is stable over the long period of self-cycling, continuous self-cyclings. And as this system can provide ensemble forecast, we also try to see if we also try to look at the benefit of this system provides the uncertainty based analysis and also probabilistic forecast. So the right-hand side shows the vertical level distribution of a HAFS-D system, and the bottom is showing the horizontal domain coverage, which is indicated by the shaded color. And in case you're curious, the green one is the HICON domain, and the right zone is the verification domain. And due to the computation resource limitation, so we have to reduce the vertical level from 81, which was used in HAFS-A, to the 65 vertical levels here. And the model top is on 2 millibars. And also the horizontal resolution for the ensemble members are 6 kilometers, and for deterministic forecast is using 3 kilometers resolutions. And the macrophysics schemes here, we're using the JFDL, and there will be no ocean couplings for the ensemble members. And the HICON coupling is only for deterministic forecast. And for the ensemble bar, we are using a hybrid of 80 GDAS members plus 20 HAFS members to provide the background. In CAP system, we're using the 20 HAFS members. And to produce the members, we perturbed the model physics, which are listed here. Those 3 model physics.
You got 5 minutes.
Oh, okay. So yeah, I know there are questions about how the observation using HAFS-DA. So this one is kind of a summarized, which is also snapshot for I think it's during Hurricane Lee time period. And this is overall what all the types of the observations, conventional observations, and the instrument that the observation comes from. This is for UV and the temperature and the pressure. So for example, the 220 is the river sound, and 236, 237 is indicate the RICOM data, and number 240 to 260, those are all satellite-derived wind, and 290 is the scarometer wind that you see here. And I also want to point out this observation type 2.241. This is the enhanced AMV data that only assimilated here in the HAFS-D. Next. So this one is showing since the very beginning of the HAFS-D system, which is in June 28th, when we kick off the system, until now, the assimilated observation numbers here. This also includes the satellite data and as well as the conventional data. So you may notice at the end of August, there's a bunch of purple kick in. This is they add in the newly crisp FSR data from the NOAA 20s. And there are a huge amount of conventional UV. Also from the very beginning, June 28th until now, the conventional observation innovations, which kind of show the DA is doing what they're supposed to do by bringing down the arm after each analysis. Next. So here we take a look at the area average, the root mean square error, bias, and STD for 500 hectopascal temperature, and verify that against the GFS and the ERA5. Actually, we want to demonstrate the stability of this self-cycling system, which can continue to run from very beginning until end of October. Next. And we also check the performance of the HAFS-D system and compare it with the operational HAFS-A and the HAFS-B, as well as the HWRF and also GFS data. So I forgot to mention that the HAFS-D didn't use any VI. Both track and intensity, but later on, as we launch the forecast, the model managed to catch up a little bit, and it can even beat HWRF here. Consider it's a self-cycling system, so we will think this is a pretty good result here. And also for intensity forecast, I would like to point out here this red line, which is a HAFS-D deterministic forecast from hour 6 to hour 36. So the HAFS-D won't have those strong bias in intensity as what we saw in the HAFS, operational HAFS A and HAFS B. Also, here we also check the ensemble forecast, and the upper panel we compared with operational HAFS A, which is indicated by the black line, and deterministic forecast is the red line. So the track forecast is not good, but I would say it's comparable. And also for intensity, again, I want to point out at the hour 12 to hour 36, it's also comparable with the HAFS A. And lower panel, we actually compare the ensemble forecast with the cloud HAFS ensemble forecast, which is Jiayi just introduced. And here, the blue line is the HAFS D deterministic forecast, and the ensemble forecast, ensemble forecast, and the red color is from the HAFS E system. So the track is a little bit better in the HAFS D. And both systems are a little bit under dispersive, but the spread of HAFS D also a little bit better than HAFS E. But for intensity, here I will see the HAFS D at the beginning, still at hour 12 and hour 36, the intensity forecast is good, but later on the arrow kind of grew larger than the HAFS E. Okay, yeah, this is my last slide. So, yeah, so I read. Yeah, we introduced about the current HAFS DA status, including the functions and the observations, and also we talk a little bit about the performance HAFS D and our purpose to running that system. So moving forward, we also want to follow the trend of join the community to transition from JSI to JEDI. But we just started this types of work. So at the very beginning of the start point, we try to see if we could use JEDI functionality to replace what the JSI used to do by starting with doing a 3D ensemble var with JEDI ensemble members and sending some conventional data. But gradually, we will add in more and more observations and add in more functionality from that provided by JEDI. But I'm sure this is a tough work and a huge amount of effort that will be invested into this type of job. So that would be all.
Thank you. We move over to ocean and waves. Are you going to? Okay. Maria was also co-author. That's why.
Hold on, bear with us a second. We're swapping computers, trying to figure out where the
Okay.
there's network. No, we're trying not to. There's network issues for those online where the audio keeps popping up. So we're trying to figure it out. The AV guy's going to come at the lunch break and do a reset.
Okay. All right, so I have a bunch of people working with us.
That should work for you now. Can we switch back to the other computer? You
Should-
should be able to.
should-
You
okay.
should be able
Here you go,
to.
yes. So I have 3 R2O plans, and the first and the most eminent is improving MOM6 simulations. That includes applying relative winds. Relative winds, and the second one is the subgrid physics. I demonstrated earlier slide that particle mixing is a little bit off compared to HICOM KPP mixing, and also I didn't show it, but it has a higher, very small viscous in the ocean interior for MOM6. I've been struggling to correct it, but still I am making not a huge progress yet. So about the ocean DA as a part of R2O, another project is I'm going to talk about this afternoon. So I'm going to 3 MOM6 and then WaveWatch 3 three-way coupling, and then bottom right is the domain, test domain that I'm going to use coupling, and then green shade is atmospheric running domain, and then MOM6 and HICOM WaveWatch 3 is within this red box and the blue boxes. Okay, I showed earlier, this one is MOM6, instead it's along the track for Hurricane Lee, at the time of the storm is located here. And then again, a cup level is the buoyancy frequencies, and the middle panel is the shear instability, and then bottom is the gradient richness number. And as I pointed out, that there are a lot of overturning takes places in the buoyancy frequencies. So at this time, I don't have a TNS profiles to support this N square estimates, but we do have sail drone observations coming from SD 1069 of that period, which is located here, and the color shade is dates. So in other words, this is September 8th, 9, all the way to 14th. So the storm sail drone is approaching toward the best track of that period, and then this is what we had got from the sail drone observations of the shear instability come. So storm is coming, and then definitely you notice that the shear instability, higher shear, moving from almost near surface down to almost 40-meter depth. Okay, so this is pretty much a sort of a mixed layer depth at the bottom of mixed layer depth. So in other words, due to the storm, lee, that instability is migrating from upper to lower depth. But we have seen this one too. But in a month 6, again, it's a shear is underestimate, just simply based on the mixed layer depth. There is no shear associated with the wind-driven parts above the mixed layer depth. So it's not working. Oh, here you go. Oh, I did already. So okay, now let's look at the sail drone observations. And then sail drone observations and the gliders sort of co-located a location over here. And then purple, light blue is a sail drone, and then this orange is a gliders, and then the red lines are the beyond the track there. So at that time in 2022 in September, so we have a set of concurrent or located observations, so that we can have a complete set of the atmospheric parts, and then temperature, and as well as the UMP components from the sail drone, and then gliders for temperature salinity from gliders. And the red curve line is distance from the each instruments. So what if, this is pretty much before Fiona. Fiona is further in the upper east, and then showing that the shear current instability at the bottom left shows that again higher values residing in the mixed layer depth, and the storm is approaching it. We do have a lot of sort of a spotty high shear values associated with surface wind for things. But in the mixed layer depth, the temperature salinity we come from, and then we saw bottom panel from the middle figures shows that the stratification is pretty much residing at the bottom of a mixed layer depth. Okay, so but in the meantime, we do have a lot of spotty values existing, but it's not exactly negative. But that is negative too. So okay, so some of them negative and some are positive. So there is an overturning takes places before storm comes in. Okay. Okay, now, so I think I showed this one in the middle panel, and then I didn't show the mixing along storm track for coming from the HICOM KPP, which is HAFS A, and then just a loose visual comparison again in a HICOM KPP doesn't have a much whiteout and then N square field, but and also, there are a lot of shear high values driven by the storm near the surface. compared to EPBL, MUM6 KPBL is less. And then shear instability values, the mixed layer depth is pretty much equivalent, I mean, same. But however, when you look at the richest gradient number, and the shape's quite different. The HICAM KPP in the mixing is pretty residing near the surface, except that the storm condition in the middle of a mixed layer depth, right? And then now take a look at the KPP. Here you go. It's a same transect as a MUM6 and then HICAM on here. And then with the different KPP mixing, we can get rid of the overturning and then N square. And the shear driven by storm is much weaker. And even in the shear at the bottom of a mixed layer, that's weaker. So, and then in terms of mixing, the distribution is pretty similar with the HICAM KPP. However, in the MUM6 KPP, a lot of mixing going on, after storm passes. Okay. So, we need to tune some parameters, to, get the better. So it turned out that with the MUM6 EPPL in the surface cooling is weaker than HICAM KPP and the MUM6 KPP. So definitely this negative buoyancy frequencies impact on the SST cooling in the upper layer. Okay, how many minutes do I have? Okay, so
About 5.
all right, so this the temperature solidity profile between EPBL and the KPP. This is a MUM6 configuration. We do have the algo profiles, eastern loop current during the Hurricane Ian period, and a lighter blue is observations, and the dark one is the models, and then for temperature, and then orange and then red are the salinity for MUM6 in a darker red, and then orange for observations. So, definitely we do have a different temperature salinity profiles that we estimated, predicted by the different mixing schemes. So in this case, it's the loop current area in the agreement with observations. And then this is the Florida Strait at the bottom level. And again, KPP seems to produce this better agreement with the temperature and salinity simulations. Okay, next. Okay, so I'm going to skip this one because I've seen it. Now, going into the three-way coupling, and then, planetary boundary layer has been really advanced, much advanced than marine boundary layer. So we're going to attack some, schematic, plots for LC interaction zones. So top panel on the right side is associated with the air movement, and the middle one is the wave has a wind sea as well as the swells, and the bottom is the ocean side. Okay, so it's ocean, again, it's more complicated too, as much as the air side, but we're going to put some wave model in it in order to take care of surface roughness and then wave and current interactions, which can be impact on CD, and the state depend on the CD. And then we do also considering critical layer where the wave speeds and the wind speeds are equal. And then above that layer, momentum can be negative. Okay, so critical layers is a sort of changing its momentum flux directions. And then we do have a heat fluxes, which break by the wave, breaking wave and the spin waves.
You want me to advance it?
That's okay. So, okay, so So first one, because we put it in the wave boundary layer, so we're gonna modify the surface roughness through these equations, okay? And then the second modification we need is the FB3 surface layer, which is velocity profiles coming from the MO similarity, but we do add the effective displacement of sea elevations. So it's a little bit modifications take places, and then this here, but when I do apply the wave boundary layer and the momentum flux is considered, this is a blue curve, is what you expected to have the middle layers. So they do have, not quite similar to the U profiles, but they do changes the profile U profiles by adding wave watch to it. So this is schematic diagrams. It's ideal cases, but this is what we expected to happen in the boundary layer. Okay, so what happens under the hurricane wind? There are two main things we have to consider into it. So limiting of aerodynamic roughness because of saturated surface slopes that is shown in the Davis et al. Using the spotter and zoo on the right side too. It's pretty much constant and for CDs. And then second one is the Stokes drift and the surface dispersion and the transport, which is shown as blue and the purples during the hurricane Ike. Oh, is Ike? No, it's not. It's 2016 15 storms over there in the Gulf of Mexico. But those are black dots symbols are representing sort of different wind conditions we have find it. Okay. So this is pretty much schematic diagram of three-way coupling based on the publication that I did. Next, and then we're going to do the spray as well. So to accomplish, so we need to improve MOM6 in order to reduce the modeling scale. And by in order to do that, we're going to do the mixing physics, improve testing, and also LC interaction and LC interaction processes. And we by AOML, it's called the Doris, and then please go and visit. It's not complete yet. It's up to 2019, and it will come observations for this database. So it's a useful tools for research purpose. Okay, and the three-way coupling is I'm gonna again replacing polynomial fitting Z0 to wave watch 3 Z0 estimate. The wave-induced mixing and the Langmuir turbulence parameterization, and atmospheric side wave current interaction due to the wave breaking and then coherent flux parameterization, and then considering the misalignment between swell and the wind. That impacts on the drag, and it will change the drag surface drag pattern depending on the wind utterance. Thank you.
Thank you, Hyunsuk. All right, we're gonna head out into the lunch break. Be back at 1:30 so we can do the group photo. Those of you online, please log in around 1:30 so we can put your smiling faces up and get the group photo with all of us in front of the screen. Thank you very much.